Here for that introduction, and today I'll be introducing AWDIT, which is 3 algorithms that significantly improve on the performance of the state-of-the-art in testing of weak database isolation. And to start off, I would like to give a motivating example to explain some of those words. So consider a chat room where we have Alice, Bob, and Charlie communicating over a database. Say that Alice poses a question and Bob answers the question. Now Charlie would be very confused if he received the answer before the question. So one way to think of what went wrong here is that the question in some way caused the answer, so therefore Charlie should view the question before the answer. And this property is in general called causal consistency, and it's a guarantee provided by databases to its clients. However, notice that concurrent writes can appear in any order to readers. And in that sense, it's a weaker database. It's a weaker guarantee. For instance, if you had 2 simultaneous questions, 2 people could see them in different orders. So you might be wondering, why do we care about these weak guarantees? Why shouldn't the database just provide the strongest possible guarantees to all of its users? Well, there are a few reasons. One of them is performance. So the database can provide higher throughput if it also provides weaker guarantees. And the one is fault tolerance, where with strong isolation guarantees, the database can similarly shut down or not be able to respond to requests in the case of network faults. And finally, we also care about it because it's often the default in real databases to have weaker guarantees. Okay, but there are some problems, which is one of them is that databases have repeatedly been shown not to actually satisfy the guarantees that they say they will give. Or they just provide simple pros as guarantees. And another reason for this is that databases are actually really complicated distributed systems. For instance, what you might think of as a single database could actually be 5 databases in a trench code communicating over the internet. And therefore, we need some way to find these errors. And one solution is black box testing, which is what I'll be introducing today. So to explain this, we need some concepts from the theory of database testing. So when we look at an interaction where some clients send some data to the database, we call this interaction a history. And so you can see we have here 3 clients that are interacting with the database, and each client is sending what are called transactions here. So you can think of transaction, if you're not familiar with the database theory, as, for instance, in a bank where you want to move some money from one account to another account. And these transactions consist of operations, which in this setting are just simple reads and writes to values such as x and y. And finally, these transactions are ordered on sessions based on each client. And now we can formally define these guarantees that I mentioned earlier as isolation levels. So formally, an isolation level is a predicate on history. So you can think of an isolation level as a function, takes in a history, and then says, is this history satisfied? And some examples here are causal consistency, which I already mentioned, read committed, which is actually even weaker than causal consistency and often the default. And then serializability, which basically says that you can view all the transactions in some order that makes sense. And this is usually what developers think the database is doing, but not what it's actually doing. Okay, so if we then want to test a database or a cluster of databases, well, we start with a database and some isolation level that we want to test it for. Then somehow we generate a bunch of transactions, some reads and writes, and send it to the database. Then we can look at what we get back from the database and collect it into one of these histories. And the final step is then to check if the history satisfies the claimed isolation level. Okay, so this leaves some questions. For instance, how do we check if a history satisfies a given isolation level? And also, maybe these bugs are very rare, so we need to maybe check very big histories or run on very many histories. And this motivates the need for very efficient consistency checking algorithms, which is what the problem is called of testing whether a history satisfies an isolation level. Okay, so I'll go over some brief relevant literature here. In the 70s, Pavlogiannis showed that checking whether a history satisfies serializability is NP complete. And this is a bit of a bummer if you want to do this at scale. But then, skipping over a bunch of important research, in 2019, Biswas and Andreas showed that these three isolation levels of read committed, reatomic, and causal consistency, abbreviated as RC, RA, and CC, are checkable in polynomial time. And then last year, Liu et al. Proposed Plume, which provide efficient algorithms for these three isolation levels that are significantly improve the state of the art in terms of real-world performance. However, if you look at the complexity, it's something like the number of transactions cubed times some other factors. And so this leaves us with some questions, like how fast can we truly test these weak isolation levels in theory and in practice? So this is where our work AWDIT comes in, which is three algorithms for RC, RA, and CC. And you can see for RC and RA, we run in n times square root n time for n operations. And for causal consistency, we run in n times k time for k sessions. And typically, the number of sessions is small in practice. So this is obviously a big theoretical improvement over the state of the art. But you might be thinking, n times square root n, that sounds a bit strange. Are you sure that's not a linear algorithm, for instance? And here we prove that AWDIT is actually essentially optimal by showing lower bounds for these three problems. We show that under some assumptions, no algorithm can do better than n square root n. But in fact, our lower bounds are not just restricted to these three problems. In fact, any isolation level that is stronger than read committed and weaker than causal consistency, this lower bound applies to. Okay, so in order to give some ideas on how we did this, we need a different view of histories. So it has long been noted that you can view histories as graphs in the following way. So we have a history here on the left with two transactions that write to X, and then another transaction reading those writes in the opposite order. Okay, so we can turn this into a graph in the following way. We add a few different kinds of edges. So on the left, you can see we have an edge labeled SO, which stands for session order, and it simply orders T1 and T2 because they're on the same session. Then we also have some blue edges called WR, which stands for write read, and those simply relate writes with the reads that read them. And finally, we have on the right the program order, which simply relates operations within the same transaction. Now, so once we have this view of histories, we can give a different formalization of isolation levels, which was also introduced by this paper in 2019. So they basically show that if you have your favorite isolation level I, then you can define it in the following way. Take some history H, and then you say this history H is consistent if I can find some total ordering of all the transactions. So you can see on the picture here we have all of the transactions in the history in some order, such that the write, read, and session order edges follow this ordering. And then there are also some constraints that are dependent on the specific isolation level. So I will give the example of read committed here, and bear with me here because this gets a little bit technical, but I'll give an example afterwards. So the rule for read committed says that when you have a transaction T3 that first reads some transaction T2, and then later reads X from a transaction T1, where T2 also writes to that key X, then T2 should come before T1 in the commit order. So just to reiterate, this is an implication that whenever you have the pattern on the left in your graph, then T2 should come before T1. And I promised an example, so here it is. We use the same history from before. And if you squint, you can see that the two pictures on the left and right are actually basically the same. In fact, if we just visually swap T1 and T2, you can see that it's actually exactly the same. So therefore, the definition tells us that T2 should be in the commit order before T1. However, remember that the commit order also has to agree with the session order. And so therefore, this cycle between T1 and T2 is actually a witness of inconsistency with read committed. And this also serves as the basis of AWDIT, where the algorithm is essentially finding triples T1, T2, and T3, like on the right here, and then remembering in a partial commit order that we call CO prime, that T2 should come before T1. And then if those those inferred edges form a cycle, then we know that the history is inconsistent. Okay, but even if you could enumerate all these patterns on the right as efficiently as possible, there could still be a cubic number of them, which would lead you to a cubic algorithm. So we have to find some clever ideas. So one of the ideas that allows AWDIT to achieve the complexity that it does is that we don't actually have to enumerate all of the triples. And I'll explain that with an example. So consider the history on the left here. We have 3 transactions writing to x, and then another transaction reading them in that same order. Okay, so we can apply our rule from the right and see that T1 should come before T2. We can do it again for T2 and T3. But actually, since the program order is transitive, we can also do it between T1 and T3. But remember that we were only interested in finding cycles. So here it is actually not necessary to infer this edge because we already have a path from T1 to T3. And so this is one of the mechanisms for how AWDIT achieves the complexity that it does by simply not enumerating cases like this. And in fact, it only enumerates O of n square root n of these triples. Okay, so we implemented AWDIT in Rust and ran some experiments. We tested it on 3 real-world databases using standard workloads. So those are scripts for generating reads and writes to the database from the literature. And then we ran it on 2 to the 10 and 2 to the 20 transactions, which correspond to at most 50 million operations. Okay, so we compare it to Plume, which is the current state of the art. And as you can see here, we have a graph with the running time of AWDIT on the x-axis and the running time of Plume on the y-axis. And so you can see that the middle diagonal line, if the points are above that line, then AWDIT was faster. And this is also a logarithmic plot. So each successive line means a factor of 10 improvement over the state of the art. So just to drive the point home, in this section we have 100 to 1,000 times speedup over the state of the art. And the picture repeats mostly for the read atomic and causal consistency levels. And you can see the numbers here as well, where we achieve on the 20% largest histories speedups of around 240, 260 times speedups. Okay, so in conclusion, we have argued that we need efficient algorithms for this problem of testing weak isolation, and that AWDIT is not only achieve this quickly in practice, but also does it so optimally in theory. And finally, the lower bounds that we use are general in the sense that they apply not only to these 3 isolation levels, but to any isolation level that you can fit in this range. And as a final remark, me and my co-author hope that more people in the PL community can use tools such as this to prove lower bounds for more problems. Thank you for your attention.
Any audience questions here? I can start with one then. So the technique you presented here lets us run a single test. Do you have any kind of principled guidance for constructing test suites that would tend to be sufficient for catching bugs?
So that's kind of outside the scope of what we are doing. We are mostly just, in this work, focused on improving the efficiency, but there are other works that do this kind of thing. Also try to run the databases in a way where they inject faults to try to provoke errors and this kind of thing.
Got it. Okay, thank you. Anyone inspired with a question in the last 30 seconds? I can try another one then. If we're using optimistic concurrency control and we might be rolling back transactions when we notice issues, does that create any interesting twists for the kind of thing you're doing here?
Not really, because we're just looking at the committed transactions mostly here, because I mean, it's pretty easy to tell, like if you read an aborted transaction or something, that's very easy to check for. So the interesting part really happens with the committed transactions.
Got it. Thanks.
I was wondering if any of the tests that you did, you also found some violations?
Yes, I actually have a bonus slide for this. So the answer is maybe, because well, we did find some histories that have violations, but we're not 100% sure that they're like bugs in the database, because like the pipeline from the database to us having a history that we can test on is quite complicated, and we're not sure if the errors maybe came in that process.
So these databases don't provide their own logging?
Okay, what do you mean by that?
So I would imagine the pipeline would be take the database, bombard it with some transactions, and then force the database to log some transactions.
Yeah, so we're not actually forcing the database to log transactions.
Okay.
We're like acting as a client, or well, we're actually using someone else's work for this, but they're using the database as a client and then logging what the client sees, basically.
Okay. So then what could go wrong in this pipeline?
Yeah, that's a good question. We haven't really thought that deeply about it, but...
So anyway, my question was about, if you find a violation, can you also pinpoint to the developer that here is where you might want to fix?
Yeah, so the tool will spit out as best as it can, like where in the history the bug happened. So it'll give you some transaction and say these transactions are wrong somehow. So you can use that to debug the database.
Okay, thanks.
Any other audience questions? Let me go for one more of mine then. So you presented this just in terms of read and write operations on some universe of objects. How do declarative queries look in this kind of setting?
So I have to say I'm not familiar with that term.
Oh, I just mean like Postgres lets you run a complex select query that could be touching all kinds of objects and use interesting logic to decide which ones are going to be touched.
Yeah. Well, so that's an interesting question, and well, I guess here we're just interested in finding bugs, so we sort of use the easiest thing possible, and this is what people have done for many years now. But there are some new research into trying to test like more complex queries as well.
And I'm thinking about implementation techniques like predicate locks, which would, I think, go with a stronger consistency level than you're dealing with here, but maybe there are similar techniques that are used for the weaker levels.
Yeah, so I mean, this kind of thing is like an open area of research, I guess. Yeah.
Okay, thanks. Going once, going twice. Okay, let's thank the speaker again.